NA typically means that that guy chose to not vote for that particular issue. Okay, and that happens. Probably he had a party to attend to, or he had a conflicting thing, and he didn't want to go against his party declaration. Whatever, he didn't vote, so those are represented as NA. In this year, in 1984, the Democrats had majority, Republicans were in minority. There were 267 Democrats and 168 Republicans in the House. Okay, so you have the voting record available. What is the question that you are trying to address? The question that you are trying to address is, suppose it's given to you that one particular congressman voted in the first vote as yes, and in the second vote as no, then what is the probability that that guy was a Democrat is the question. Can you look at the voting patterns and identify whether he was a Democrat or Republican? Do you think that's possible? Of course it should be possible. It should be possible because you know how generally Democrats have voted, how generally Republicans have voted. So based on this voting pattern, you can guess whether that particular person voted yes or no. That's something that should be doable. We are going to, this intuition that you have, the reason why you are saying it is, you can look at the probability of voting yes when someone is a Republican, and the probability of voting no when someone is a Democrat. This idea you have, what you are doing in your mind is using Bayes regression. What you are doing in your mind is not logistic regression. What you are using in your mind is Bayesian this thing, and that is the method that we are going to adopt and try to solidify and go ahead and use the math and do it. Okay. Now, before starting this problem, before trying to look at the voting analysis and all of it, very blindly you can make a guess. You are talking about some pattern, you are asking whether that person is a Republican or a Democrat. You know what? Originally, we know that there are 267 Democrats and 168 Republicans. So if you are asking a question whether someone is a Democrat or a Republican, he is more likely to be a Democrat rather than Republican, because just because this random person you pick is more likely to be a Democrat. Right? You call this as the prior probability. You have some prior information. Without even looking at the features, you are able to make some particular claim about is that person likely to be the same. I mean, if I ask you a question without telling anything, is that MP likely to be corrupt or not? Your answer is going to be yes. I mean, there's some prior information. You have your prior belief, right? Bayesian algorithm is one of those algorithmic methods which allow you to feed in your prior probabilities and prior beliefs. And based on the current set of evidence, you can modify your current beliefs. This is a method that allows you to do that. And so it's got a lot of appeal for problems where you do not really have huge amount of data to absolutely be certain about one particular issue, right? So where you can manually feed in your prior beliefs to make some final judgment calls. Use your prior belief, use all the data that is available, and together make a combined statement. Naive Bayes algorithm is one of those algorithms which allow you to do that. Okay, so the question is, even though our prior belief suggested that it's a Democrat, now we want to use the features and find out whether we can do better. Can we do better? Of course we can do better. What we are going to do is look at the voting patterns of each one of the issues. The question was, in issue 1, so you guys can read this, you know what this means, right? The symbol means. What does the symbol mean? Given in the first issue someone voted yes, and the second issue someone voted no, what is the probability that he is a Democrat? That's what this conditional probability is, right? It's important to be able to read the notation because we are going to do a lot of this notation in the next few slides. So we are interested in first vote being yes, second vote being no. Just remember those numbers and we'll move on to the next slide. So what I have here is votes for whether the first issue. Okay, overall, that handicapped infants issue, that vote failed to pass, okay, with 236 to 187. Okay, 236 people voted no and 187 people voted yes for that. It failed to pass. Now, let's look at how exactly this vote happened. We are trying to find out whether it was a Democrat or Republican, right? So we need to look at how did Democrats vote in general, how did Republican voted in general. So I'm splitting that vote here. This is Republican votes. Most Republicans voted no. Okay. Democrats in general voted yes, but they were not as violently skewed. Here Republicans were certain it's a no. Democrats were like, there were some people who were no, some people who were yes, but overall they voted yes, right? So this is a probability that we can estimate, which is probability. What is this? Can you read this for me? Given is Republican, what is the probability he voted yes? That's what we are doing here, right? That number, you can look at the voting number and get that. That is 31 by 168. In this case, given a Democrat, probability that he voted yes for that issue turns out to be 156 by 267. Okay. Similarly, for issue 2, I can compute. Issue 2 was, it passed in a very narrow margin, 195 to 192. Okay. And you have these yes and no's, and I can compute the probability. For Republican, given a Republican, what is the probability he voted no? Because for issue 1, we wanted yes, and issue 2, we wanted no. So this is issue 2, I'm computing probabilities for no. I'm computing these numbers. Okay. Bayes relationship. This was the Bayes relationship. Probability given B, probability of A given B can be expressed as probability of B given A. Okay. For this problem, that particular issue translates as follows. What we are trying to find out is, given that this guy has voted yes in 1 and 2 in no, what is the probability he is a Democrat? I can translate that to the following. Probability that given a Democrat, what is the probability that he voted yes in 1 and no in 2? Fine? Simple Bayes rule. Here is the simplification that naive Bayes makes. What naive Bayes makes is this probability that we did. This is a joint probability, right? It's going to make an assumption that these are independent voting events. Voting in 1 does not affect in voting in 2. That's clearly wrong. People have some principles, even though you might not believe it. I mean, they have some principles. He is voting voting in 1 has some dependence to voting in 2. That is there. But naive Bayes makes the assumption that they are independent. When they are independent, we know that the joint probability can be expressed as a product. We know that. This is the key assumption that naive Bayes makes. Why do we have to make the assumption? This is easy to evaluate. This is easy to evaluate. So I can take a product and make an estimation of that. But this together is harder to evaluate. So naive Bayes makes this particular assumption. After I do that, the equation becomes this. Okay. Now, what are we really trying to do? I'll show you if it moves forward. Oh, there. Okay. So this is the equation. We are trying to find out, given this voting pattern, is he a Democrat? Or given this voting pattern, is he a Republican? That's what we are trying to do. Whichever probability is higher, we are going to say that is going to be that class. Correct? For both of these, the denominator is exactly the same. Right? So all we need to do is focus only on the numerator part. Okay? So the way coding is done inside the naive Bayes algorithm is it codes only the numerators in each one and compares whichever one is biggest and it assigns it to that particular class. Okay, that's about implementation detail, because there's no reason to compute the probability. This one is irrelevant at all, so it doesn't bother computing that particular probability. So let's go ahead and compute this. I've already computed each one. Probability of being Democrat, we know, because we know how many Democrats are there in the total house. So we know this, we computed this first. Probability of being a Democrat and voting yes, we also computed in the first slide. This was in the other slide. Put all of those numbers. This number turns out to be 0.15 for the Democrat, turns out to be 0.03 for Republican. So I'm going to say this is to be assigned in Democrat. Is the idea clear? Nowhere have I used a complicated training algorithm. Nowhere did I have to assume a sigmoid shape relationship. I managed to do classification without making any of those assumptions. Right? All I used is naive Bayesian relationship, and I've assumed independence so that I can break up that probability. When I break up the probability, I'll be able to do all of this. This is exactly what naive Bayes does. Yeah.
Because we assume that independence, we broke it and we simplified.
Correct.
If we don't do that, we go ahead with the as usual Bayes formula.
Right.
And computer can calculate in fact why we need it.
So the real problem that we are in all of this, right? These are all illustrations, right? With two cases. In the real world data set, what happens is, for example, you are trying to do, given this set of words, is it going to be in the art section or each one of the section? So the possible set of words is huge, right? You are trying to have to compute these joint probabilities based on when are this word and that word and that word and that word all occur together. The number of instances where they all occur together might be very small, but you can make the number of times a single word occurred might be large. Therefore, you have more data points to make those judgments than trying to search for data points when all of them happen to occur together, and in those cases find out whether Democrat or Republican might be harder. So naive Bayes makes that relationship assumption for a reason, and it's precisely that assumption allows it to handle the problem of multiple classes a lot more easily. Yeah, but there are variations of that where you can prescribe a relationship between this one and that one too. So my naive Bayes algorithm allows you to prescribe a prior belief, and it also allows you to give you naive Bayes allows you to prescribe a prior belief, but there are other Bayesian methods which allow you to specify relationship. Once you specify a relationship, it's no longer called naive Bayes. Yeah. Correct. So you're using a model, but that model is based on your understanding of that physical process. Logistic was a fixed sigmoid curve for all of them, right? This is better. You're using a domain expertise to prescribe a relationship. So for this particular problem, you can prescribe something that is more relevant. That's the assumption. Yeah.
We don't need to build a model.
You do not need to build a model. That's the beauty of this. Absolutely. That's the beauty of naive Bayes. And I'll show you when we run this, it doesn't actually, you will be calling the same things, just like we call GLM, you'll be calling a function like that. If you look at the output of the function, it will have all of these probabilities pre-computed. And whichever one you ask, it will multiply the probability and give you the answer. It's very simple model, and which is why it's intellectually appealing model too. This is the first time we are explicitly discussing that it's a probabilistic method in class. Probability is being used in all of them as well. Generalized linear model it uses, but it was all behind the scenes. Here it is simple enough that we can I've explicitly written out the algorithm for this. That luxury we don't have for any of the other models. So no parametric feat needed to compute this. Very simple, right? And which is why this is actually very appealing. Let me quickly show you how you implement this in R. So we'll talk about that in a bit. This is generally used in these multi-class problems. Typically, logistic regression doesn't do well when you have those large number of classes problem. This one does better. But like always, it's never a clear-cut answer. It depends. Depending on this type of problem, these do well. Small classes, I'll happily use logistic regression. The naive Bayes algorithm is coded in this library, E1071. I have no idea if there are 1070 and 1069 versions exist, or if 1072 is better. I don't know why they called it that, but that's the one it's there. So what I have done here, all the piece of code that I have done is I've done imputation of missing votes. Okay, I'm not going to talk about that. The code is here. Please do look at it. What is the value? What is the way we can impute the vote? If some guy, which party he belongs to, you can find out how did that particular party vote on that issue, and you assume that that guy also voted the same way based on the party, which is what happens in majority of the times. So you impute it that way. I have shown you the code of how to do all of that. I don't want to discuss that in class because we are running out of time. Sorry? So this is the way you impute the model. So this is the way you train naive Bayes. You are training with class, Republican class or whatever is what you want to find out. And I'm providing that data. Now let's look at what is stored in the model, right? NB model. Let's see what is stored. So, what is stored in the model? A priori probabilities. What is the probability of being a Democrat? What is the probability of being Republican? These are the same steps we discussed in class, right? Without, you give a prior probability and we give this thing. Then conditional probabilities for vote 1. How did the Democrats vote? How did the Republicans vote? Yes or no? Each one of those voting issues, it computes these conditional probabilities. And when you ask to predict, it does the same multiplication we had to do, and it gives you that particular prediction.
What is that point?
This, actually that's a good question. I don't know. I'll check. I'll check. Sorry, yeah. Somehow my eyes focus only on this side. I haven't, do you know what this Y is?
Probability of that particular, okay.
All of them have.
It should be both N and Y. It should be given for both N.
Yeah, but it's actually giving, everything is Y, so I don't know what. Yeah.
No, prior probability for only Y it has given. Ideally, N.
Huh. I'll check and tell, or actually Gautam is a better person to, answer this. So please do check. So, and the way you run the test is simple, exactly like always, predict function, and you run it. And in this case, it gets 86% correct prediction. So, as I promised, it was a very simple idea. Naive Bayes, easily explainable, no complexity in that. So the key assumption that naive Bayes makes is the independence of the features. That is a very key assumption that it makes, and it's almost never true, right? But you know what? It works surprisingly well. It surprisingly, it works well for that domain of problems which we talked about. Text classification. This is a topic that's normally discussed when people discuss text mining. But since we are talking about classification, we thought we'll introduce the idea right now here itself. Okay, so it works well when all the features, the predictor variables, are categorical predictors. That is when it works the best. It can, however, also be used in numerical case, but the algorithm itself was not designed for that. How do you use it in numerical case? What it does in the background, depending on the algorithm that you are dealing with, it might bin the numerical values into different categories and then use the same thing. Or it might assume a normal distribution, and based on the normal distribution, it gives you probabilities for each value. Ultimately, you need to compute probabilities, right? In that case, it assumes a normal distribution and computes those probabilities. But it best works when you have categorical predictors. Okay. So there is one more topic I wanted to talk about, but I'm going to stop here with that. We will talk about time series forecasting in our next class. So let me summarize what all we have talked today. Today was a very dense class. We talked about three major ideas. The first concept we talked about was principal component analysis. Principal component analysis allows you to look at the X variables, the feature set, and it gives you a method to transform the feature set into new variables, where each variable, it allows you to order the variables with most information to least information. What I mean by information here is variance, by largest variance to lowest amount of variance. This allows you to drop the ones that have very small amount of variance, and usually it does well because of that. Okay, but there is no guarantee that PCA will do well in the forecasting, because these decisions were made without referring to Y at all, right? It's mainly used for dimensionality reduction in problems which are typically large dimensional problems. Okay, the second method that we talked about, second big topic we talked about, is regularization, where we motivated regularization by our intuitive need to go towards simplicity rather than complexity. We had this notion that simpler models perform well and generalize well over test sets than in more complex models. So we wanted to have simple models. But complex models are needed because you want to allow for the possibility that complex models fit it very well. Regularization provides you a way to balance those two needs. We talked about two separate ideas of regularization: ridge regression and lasso regression. Both of them do it in a slightly different way. Lasso has an advantage where, as the value of lambda increases, it sets features coefficients to be actually 0. So lasso regression is often used for feature selection in place of step AIC. Compared to step AIC, this is also much more efficient process, and generally it's used in large dimensional problems, and it does it much more quickly than what step AIC does. However, ridge, even though it doesn't allow coefficients to go to 0, it also has its place. It gives generally more stable models. It works well in the case where you have multicollinearity, very strong multicollinearity situations. It does well. It gives you a unique solution. Instead of randomly picking one of those three options that we talked about here, instead of randomly picking one of those three, it gives a unique solution. Right? If you don't know which one to use, there's also a combination that's that's available. Elastic net is a combination of both ridge and lasso regression. The final concept we talked about today is naive Bayes learning method. which is a simple probabilistic method for trying to compute, given a set of features, which class does this belong to. The idea was something that we already talked about when we discussed probability in stats class. Okay. Once you do labs on all of these, you will feel more comfortable with this concept. What we are going to be talking about in the last class of this module is time series forecasting. Time series forecasting, that is going to be, how do I say, hard class. The ideas that we're going to be talking about variety of complex ideas, but again, there's only so much you would understand while you're the theory of it when you're doing it in class. But when you work the problems, you'll see how it's used, and usually after lab, people feel very comfortable about the methods that are used. Okay, I will send out maybe tomorrow or day after the set of topics that we are going to be covering in the time series class, and I'll also send you a couple of links which talk about time series methodology. I'd strongly encourage you to read up before you come to class. It will really help with understanding. Okay, so have a nice week. I'll see you guys next week.